Okay, let's unpack this. In our digital world today, it often feels like we have to constantly broadcast sensitive personal information just to prove one small specific detail about ourselves.
Yeah, it really does.
Think about showing your full driver's license, which has your address, birth date, maybe organ donor status, just to prove you're over 21.
Right. Or, handing over detailed financial statements just to prove you can afford something.
And every time you share that detailed data, you increase its vulnerability.
It's a fundamental tension, isn't it? You need to establish trust or eligibility, but the standard way is by exposing far more information than is strictly necessary.
And that information then lives somewhere else, potentially insecurely.
Exactly.
Exactly. And the sources you've brought for this deep dive point to a powerful technology that aims to, well, flip that script entirely. Zero-knowledge proofs, or ZKPs.
Right, ZKPs. The core idea, the really mind-bending part, is that with a zero-knowledge proof, one party, the prover, can convince another party, the verifier, that a statement is true. But here's the kicker. Without revealing any information beyond the fact that the statement is indeed true.
So you prove the truth, but leak nothing else about the data underneath.
That's it. You prove the validity, full stop.
It's kind of like proving, the combination to a lock without ever telling anyone the numbers.
Yeah, that's a good way to put it.
You just open it, and they're convinced you know the secret. But the secret itself stays hidden. The sources make it sound almost, well, magical.
That ability to prove only the validity is the key insight ZKPs bring. So our mission in this deep dive is to dig into the sources you've shared to really understand what ZKPs are at their heart.
Okay.
How they actually manage this mathematical feat, the infrastructure and hardware that powers them, and importantly, where they are already making a real impact.
Right, across fields like blockchain, identity, even AI.
Exactly.
So at its most basic, what are the components of this proof without revealing?
Well, you have the prover, the verifier, and the statement.
The statement.
Right. And this statement is essentially a claim that can be represented mathematically. Think like knowing the solution to a puzzle, or proving you correctly ran a piece of code, or showing you meet some criteria.
And the big shift from traditional proof is that you don't have to show the how or the underlying data, just that it's true.
Precisely. Traditionally, you'd reveal your entire bank balance to prove you can afford the house.
Yeah.
With a ZKP, you could prove you have at least the required amount, or even exactly the required amount, without revealing the total number in your account.
You prove the condition is met, not the specific value.
Got it. Exactly.
Now, the sources highlighted one specific type of ZKP that's particularly important for current applications. zk-SNARKs, that's a bit of a mouthful.
Yeah.
Succinct, non-interactive argument of knowledge.
Yes, it is. And each part is important. Succinct tells you something about the proof itself. It's really small in size, and the verification is super fast.
Much faster than rerunning the whole computation.
Oh, much faster. And non-interactive is crucial for practicality. It means the prover sends just one single proof.
One shot.
One shot. The verifier can check it immediately, no back-and-forth communication needed. This is a big improvement over earlier ZKP designs that needed multiple rounds of challenges.
Okay, non-interactive makes it much easier to actually use in real systems. The sources use some great analogies to explain this. The Where's Wally one really stuck with me.
Ah, yes, the Wally example. Imagine a giant Where's Wally poster. You want to prove you know exactly where Wally is, but you don't want to give away his location.
Right. So you could place a large sheet over the poster with just a tiny hole cut out.
Uh-huh.
If you know where Wally is, you could position the sheet so the hole is directly over him. Then you show the verifier just that little glimpse of Wally through the hole.
And the verifier sees the bit of Wally's stripes or whatever, and they're convinced you know his location because you precisely aligned the hole.
But crucially, they still have no idea where on the giant poster Wally is actually located.
Exactly. That's a great visual for the non-interactive knowledge-proving aspect. It shows you know without revealing the location.
Another analogy mentioned is the locked safe, though the sources note this one is more of an interactive example. It's about proving you belong to a secret group that shares a safe combination.
Right. You put a secret message in the safe. You challenge someone claiming to be a member to open the safe and retrieve the message.
Okay.
If they can, they prove they know the combination, they possess the knowledge without ever speaking the combination out loud.
But to be really certain they weren't just lucky, you'd probably have to repeat that process, maybe with different messages. Make them do it a few times.
Exactly. That back and forth makes it interactive. The clever math behind SNARKs allows you to achieve that same level of certainty, or even higher, with just one interaction.
Just one proof.
The prover sends one proof, and that's enough. Much more efficient.
Got it. So how does this clever math actually work? How do you take something like, I am over 18, or this transaction is valid, and turn it into something you can prove without revealing the details?
Well, it starts by translating the statement or the computation into a specific mathematical structure that ZKPs can handle. The sources get into a couple of key concepts here.
Okay, what are they?
First, you work within finite fields.
Finite fields.
Yeah, think of this as doing arithmetic, but instead of using infinite real numbers, you're using a fixed set of numbers, usually 0, 1, up to P1, where P is a very, very large prime number.
Okay.
Any result that goes beyond P1 just wraps around using the modulo operation. This structure gives you properties essential for the cryptography to work securely.
Right, a contained set of numbers that behaves predictably under arithmetic. Makes sense. And then how do you represent the actual computation or statement within this field?
So computations are often represented as a rank 1 constraint system, or R1CS. The insight here is that you're breaking down a complex computation. Even something like verifying a whole program ran correctly into a massive system of relatively simple linear equations, or constraints.
Like a huge checklist of mathematical rules the computation had to follow step by step.
Exactly like that. Each little step or operation in the original computation gets mapped to one or more of these constraints. The sources describe it using matrix notation, which looks complicated, but the core idea is verifying individual linear parts.
So if your original computation had C equal AB, maybe?
Yeah, exactly. You'd have constraints that basically check that ABC equals 0. You introduce variables for inputs, outputs, and even intermediate witness values that the prover knows but doesn't reveal.
So you're taking a program or a condition and turning it into this huge set of interconnected mathematical checks.
Precisely. Now, to make this R1CS suitable for a succinct proof system like a SNARK, you enter what they call the back-end phase. This is where the R1CS representation gets transformed into something called a quadratic arithmetic program, QAP.
Okay, QAP. Why the change? What does QAP do?
It uses polynomial equations.
Polynomials. Why the leaped polynomials? What's the advantage there?
This polynomial transformation is absolutely critical for SNARKs. It allows the entire set of R1CS constraints, potentially millions of them, to be encoded efficiently into polynomial equations.
Okay.
And the magic is that verifying if all those individual constraints are satisfied simultaneously can be reduced to checking properties of these polynomials at a single random point.
So checking one polynomial equation or related checks is much faster and produces a much smaller proof than checking potentially millions of individual linear constraints.
That's the fundamental insight that enables succinctness. It compresses the verification work dramatically. This mathematical representation, the QAP, is then fed into a specific cryptographic proving system, like Groth16 or bulletproofs, which uses things like elliptic curve pairings to generate the final tiny proof.
Wow, okay. That really is turning computation into a different kind of math problem to make it verifiable in this privacy-preserving way. But doing this at scale, making it accessible to developers, must require more than just the core algorithms, right? What kind of infrastructure and tools are needed to build on this?
Yeah, absolutely. A key piece emerging now is the zero-knowledge virtual machine, or ZKVM.
A VM specifically designed for ZKPs. Why is that needed? Can't you just prove any computation?
Well, the motivation is enabling trustworthy private computation for more general complex programs, especially in places like blockchain or secure cloud environments. A zk-VM is designed so that any program run inside it can have an efficiently verifiable proof generated for its correct execution.
While keeping the program's code and the data it processed private.
Exactly. It essentially makes arbitrary computation ZK provable. It acts like a programmable ZK circuit generator.
So you could run a complex program like, I don't know, verifying smart contract logic or some data analysis inside the zk-VM, and it spits out a proof that says, yep, this program ran exactly as specified, produced this output, but I won't tell you the specific inputs or internal steps.
That's the goal. It handles the complexities of managing memory, instruction sets, error handling, all while ensuring every step is traceably provable.
Seems powerful. Are there catches?
There are challenges, yes. The sources point out that even within a zk-VM, operations that seem simple in regular computing are surprisingly complex to implement efficiently and prove in a ZK context.
Like what?
Things like checking if a number is within a certain range, a range check, or performing bitwise operations, like the ANDs and ORs used in hashing algorithms.
Why are those hard? They seem basic.
It's often because ZKPP systems prefer working with large numbers in these finite fields we talked about. They're not inherently optimized for fiddling with individual bits, so doing bitwise stuff can lead to significant computational overhead, lots of constraints.
That makes sense. You're adapting computation designed for bit-level operations to a system optimized for field arithmetic. Are there examples of these ZKVMs out there?
Sure. Starkware's Cairo VM, designed for their zk-SNARK system, is a prime example mentioned in your sources. It's built to be a general-purpose computational model.
Okay.
Programs written in their Cairo language are compiled down, first to Sierra, then to Chasm, run by a runner, and then a Stark proof is generated for the whole execution trace.
Okay, so specialized VMs are part of the puzzle for broader usability. What about making it easier for developers to actually build ZKP applications without needing a PhD in cryptography?
Right, that's crucial, and that's where libraries and frameworks become absolutely essential. The barrier to entry for writing ZKPs from scratch is incredibly high.
Yeah, I can imagine.
You need deep expertise in crypto primitives, elliptic curves, the specific ZKP protocol details. It's a lot. Libraries provide reusable components.
Like pre-built building blocks for ZKP applications.
Precisely. They offer cryptographic gadgets. These are pre-built, verifiable components for common operations or parts of computations. Think of things like checking a digital signature or performing a hash function, all designed to be easily plugged into R1CS representation.
So you don't have to reinvent the wheel for basic crypto operations inside your ZKP.
Exactly. They also provide standard implementations for elliptic curve operations, which are fundamental to many SNARKs. By providing these modules and tools, they abstract away a ton of the complexity.
Makes sense.
It promotes code reusability, accelerates development dramatically, and helps foster collaboration because people can build on shared, verified components. The sources mention languages and tools like Circumlib, Noir, and Leo in this space, helping developers build these circuits.
Abstraction is always key for driving adoption in any complex tech, isn't it? Now, even with optimized software and VMs, the sources make it really clear that generating these proofs can be computationally heavy, like really demanding.
Oh, it is. The process involves intensive mathematical computations. We're talking about lots of hashing, things called multiscalar multiplications, MSMs, on elliptic curves, and number theoretic transforms, NTTs, which are basically fast Fourier transforms adapted for finite fields.
Okay, sounds intensive.
These operations require significant processing power and memory. This performance bottleneck has been a major hurdle for wider ZKP adoption, limiting where they can be practically used.
So naturally, the tech world is looking at hardware acceleration, using specialized chips.
Absolutely. It's seen as critical. The idea is to use specialized hardware components to drastically speed up these specific compute-heavy ZKP operations.
What types of hardware are proving useful here? I saw GPUs, FPGAs, and ASICs mentioned.
Those are the big three being explored, yeah. GPUs, graphics processing units, are probably the most accessible. They're widely available, relatively cost-effective.
And good at parallel tasks.
Exactly. They're great at parallelizing tasks, which is really useful for things like MSMs. Development is also generally faster on GPUs because the software tools are mature. The downside, they can be quite power-hungry, and efficiently managing data movement for operations like NTTs can still be a challenge.
Okay, so parallel power is their strength, but maybe less efficient for certain sequential or data-heavy tasks.
Yeah.
How about FPGAs, field programmable gate arrays? Those sound more specialized.
They are. FPGAs are reconfigurable hardware. You can essentially program the chip's logic gates to perform specific operations very efficiently. This makes them potentially faster than GPUs for certain computations, especially those with complex data flows like NTTs if you implement the logic directly.
More tailored for specific ZK tasks, then?
Potentially, yeah. They also tend to offer lower latency for streaming data. They're more flexible than ASICs because you can reprogram them, which is good for prototyping or adapting to evolving ZKP algorithms.
What are the trade-offs?
Well, their development process is complex, requires specialized hardware description languages and skills. They're generally more expensive and less readily available than GPUs.
Okay, so more tailored, more flexible than ASICs, but harder to program and pricier than GPUs. Which brings us to ASICs, application-specific integrated circuits. These are the custom-built chips, right? The Formula One cars of hardware.
Pretty much. ASICs are designed and physically fabricated for one single purpose in this case, running ZKP computations as fast and as energy efficiently as possible. Because they are hardwired, they potentially offer the absolute highest performance and best power efficiency.
Sounds like the ultimate goal. What's the catch?
The catch is, well, everything else. They have immense upfront costs for design and manufacturing, very long development cycles, often over a year, maybe 18 months plus, and crucially, zero flexibility. The logic is etched in silicon. If the ZKP algorithm changes significantly or you find a bug, you might need a whole new chip. It's a huge investment and risk.
High risk, high reward then. But the shared goal across all these hardware approaches, GPUs, FPGAs, ASICs, seems to be making that proof generation dramatically faster.
Precisely. Orders of magnitude faster. The sources emphasize that for ZKPs to become truly ubiquitous, moving beyond current niche applications, the speed of generating proofs needs that kind of leap. Hardware acceleration is seen as a crucial path to achieving that.
So we've journeyed from the fundamental concept and the kind of mind-bending math behind ZKPs through the software tools and the hardware needed to actually power them. Now, let's shift focus to the impact. Where are we seeing zero-knowledge proofs actually being deployed and making a difference in the real world today?
Yeah, this is where it gets really interesting. Without a doubt, blockchain has been a massive proving ground and, frankly, an accelerator for ZKP adoption.
Okay, and how is that playing out? Privacy seems like such a natural fit given the core ZKP concept we started with.
It is, and that's one major area. Layer 1 blockchains like Zcash pioneered this. They use zk-SNARKs to enable privacy for transactions.
How does that work?
Users can choose to make shielded transactions where the sender, receiver, and the amount are all encrypted on the public blockchain. But crucially, the transaction includes a ZKP that proves the transaction is valid according to the rules no double spending, inputs, match outputs, etc., without revealing any of those encrypted details.
So the network can verify it's legit without seeing the sensitive data.
Exactly. It offers a level of confidentiality not present in most public blockchains like Bitcoin or standard Ethereum. And the verification of these proofs is very fast, often just milliseconds. Though it's important to note Zcash privacy is optional, unlike some other privacy coins.
Okay, so that directly addresses the transparency issue inherent in many public ledgers. What about another huge challenge in blockchain? Scalability. Getting more transactions through.
Yes. ZKPs are fundamentally changing blockchain scalability through layer 2 solutions known as ZK rollups, particularly prominent on Ethereum now.
Rollups. How do they use ZKPs?
Okay, so instead of processing every single transaction directly on the main chain, layer 1, which gets congested and expensive, ZK rollups bundle thousands of transactions together off-chain.
Okay.
They process them there, figure out the final state change, and then they post just a small summary of that resulting state change, like an updated account balance tree root, plus a single tiny ZK validity proof back to layer 1.
Wait, so layer 1 doesn't have to re-execute or even store all those thousands of individual transactions.
Yep.
It just verifies this one proof that guarantees the entire batch was processed correctly according to the rules.
Exactly. The L1 smart contract receives the compressed state data, and the proof quickly verifies that proof, which is cheap to do, and updates its state based on the confirmed off-chain computation.
Wow.
It offloads enormous computational burden from the main chain, enabling significantly higher transaction throughput and lower fees.
That sounds huge for usability.
It is. The sources point to rapid growth in this area. Projects like SexSync-Era, StarkNet, Polygon ZK EVM are seeing substantial investment in usage. You can see it in their total value locked TVL figures.
And you mentioned StarkNet, they use Starks instead of SNARKs,
Yeah.
right? Is that a big difference?
Yes, StarkNet from Starkware uses zk-SNARKs. Snarks have some different properties. They don't require a trusted setup ceremony like many Snarks do, which some see as a security advantage. They're also thought to be potentially resistant to quantum computers, although they tend to have larger proof sizes than Snarks currently.
Interesting trade-offs.
And Starkware has also developed their own language, Cairo, optimized for Stark proving, and built-in features like native account abstraction. It's a slightly different flavor, but the core idea is the same, using ZKPs for scalable computation.
Okay, so we've covered privacy and scalability within a single chain. What about connecting different blockchains? Cross-chain bridges have had some pretty bad security vulnerabilities.
Yeah, that's been a major pain point. And ZKPs are starting to address this in interoperability with ZK bridges.
ZK bridges. How do they work?
Traditional bridges often rely on a small group of trusted validators or complex multi-signature schemes to attest that something happened on chain A so an action can occur on chain B. These can be central points of failure or attack.
Right.
ZK bridges instead use SNARKs to verify the state of one blockchain on another in a trustless manner. Basically, they generate a ZK proof on chain A, proving some event occurred, like tokens being locked, and that proof can be efficiently verified by a smart contract on chain B.
So chain B knows for sure the event happened on chain A just by checking the proof without trusting intermediaries.
Exactly. It enables secure, efficient communication and asset transfer between networks. Projects like Telepathy and ZeekBridge are mentioned as innovators in this space.
That sounds like a significant security upgrade for the whole cross-chain world. Where else in blockchain are ZKPs making waves?
Decentralized storage is another big one. Schemes like proof of storage allow a user, or rather a storage provider, to prove they are correctly storing a specific piece of data over time without having to constantly reveal the data itself or transfer it.
How does ZKPs help there?
Filecoin is a prime example. They use zk-SNARKs to make their storage proofs, called proof of replication and proof of spacetime, highly efficient. They compress proofs that would otherwise be hundreds of kilobytes down to just around 192 bytes.
Wow, that's tiny.
Yeah, that compression is critical for making a decentralized storage network scalable and affordable. There's also Herodotus, which uses Stark proofs to bring verifiable historical Ethereum data on-chain, which wasn't easily accessible before.
Okay, and quickly, what about enterprise uses or proof of reserves?
Right. In enterprise or supply chain settings, ZKPs can verify product authenticity or compliance within permission blockchains without revealing sensitive business history or proprietary data. And proof of reserves, ZK-POR, is becoming important in finance, especially crypto. Exchanges can use ZKPs to prove they hold sufficient assets to cover customer liabilities without disclosing specific account details, balances, or total amounts, addressing solvency concerns privately.
Projects like Provisions are working on this.
It's clear ZKPs are becoming foundational for many key advancements in the Web3 space, enabling things that were previously impossible or just too insecure. But what about outside the public blockchain world? Is the impact spreading?
Oh, absolutely. And this is where the technology gets incredibly exciting for broader applications, potentially impacting everyone's digital life. One cornerstone use case is digital self-sovereign identity, SSI.
SSI. That fits perfectly with the ZKP principle of selective disclosure we talked about earlier, right? Exactly. Proving something about yourself without revealing all the source data. Instead of showing your full driver's license, which has your address, exact birth date, everything,
Yeah.
you could use a ZKP generated from that credential to prove only that you are over 18 or only that you reside in a certain state or only that you have a specific certification.
Without revealing your name, your actual age, your address, or any other detail on the document.
Precisely. It puts the individual in control of what specific attributes they share for any given interaction.
Right.
You can verify just the necessary piece of information, maybe under custom conditions, without oversharing.
That feels like a necessary evolution for digital privacy.
It really does. Projects like HyperSign are building solutions for privacy-preserving KYC, Know Your Customer, using ZKPs combined with these SSI protocols. As your sources note, the need for strong privacy and digital identity makes ZKPs almost uniquely suited for this kind of selective disclosure.
Okay, that's huge for identity. What about in the booming field of artificial intelligence? AI is everywhere now.
Right, and zero-knowledge machine learning, ZKML, is a really cutting-edge area exploring this intersection. ZKPs can be used to protect privacy during both the training and, perhaps more immediately, the inference phase of machine learning.
How so?
You could, for example, prove that a specific prediction made by an AI model is correct, meaning it followed the model's logic exactly, without revealing the model's internal parameters, which might be proprietary, or the specific data input used for that prediction, which might be private user data.
Or maybe prove that a piece of content, like an image or text, was definitely generated by a specific, trusted AI model without revealing the model itself. Could that help with deepfakes or proving authenticity?
That's a key potential application people are excited about, yes. Adding verifiable trust and provenance to AI outputs while maintaining the privacy of the underlying sensitive data or the valuable model weights. It's complex, but researchers are exploring innovative techniques like zkDL for handling tricky neural network operations like activation functions, and projects like Kaizen aiming for scalable verification of model training itself.
Fascinating. Any other unexpected places ZKPs are showing up?
Yes, several really interesting examples came up in the sources. In fighting disinformation, ZKPs can be used to authenticate transformations applied to digital media. Like, you could prove that an image was only cropped or resized in a certain way without revealing the original full image.
So you can verify its history or integrity without showing the source. That's incredibly relevant today.
Definitely. They could also bolster secure electronic voting systems. Imagine being able to verify that all encrypted ballots were counted correctly and the overall election tally is accurate, all without decrypting individual votes and compromising voter privacy.
That's been a holy grail for e-voting.
Yeah, and in collaborative computing, ZKPs allow multiple parties, say, hospitals researching a disease, or businesses wanting to analyze market trends to collectively compute a function, or analyze aggregate results over their combined private data sets without any party revealing their individual inputs to the others.
That's huge for research and partnerships where data sharing is tricky.
Absolutely. And one more, proving software exploits. Security researchers can use ZKPs to demonstrate the existence of a vulnerability in a system to the vendor, proving they can achieve something bad without having to disclose the sensitive details of their specific exploit code.
So they prove the vulnerability exists without giving away the weapon.
Exactly. It protects their findings while still prompting the necessary fixes from the vendor.
That's an astonishing breadth of potential applications. I mean,
Yeah.
it really feels like ZKPs could fundamentally change how we interact digitally in so many ways. But it also sounds like there are still significant challenges to overcome before all this becomes mainstream.
Oh, for sure. There are definitely hurdles, and the sources were clear about these. One is often referred to as the Holy Grail problem, or maybe just a difficult balancing act,
Which is,
finding the perfect balance between the cost of generating a proof computationally, the time it takes to generate it, and the size of the resulting proof. Currently, optimizing for one, like getting a really tiny proof size with SNARKs, often means making trade-offs on the others, like requiring more prover computation or a trusted setup.
so getting a super fast proof might make the generation cost sky high, or the proof itself might be larger, like with Starks sometimes.
Kind of, yeah. There are always trade-offs with the current systems. Another major challenge is the sheer computational complexity involved. We talked about the math, finite fields, R1CS, QAPs, elliptic curves.
Yeah, it's not simple.
Exactly. This intricate math means developing ZKP applications and integrating them into existing systems is difficult and requires specialized knowledge. This impacts scalability, especially for very large or complex computations. Then there's also a significant space bottleneck mentioned. Proving systems, especially for complex computations like in a ZKVM, often need to track the entire state of the computation or the virtual machines step by step to build the proof. This can require vast amounts of memory, becoming a practical limit.
Is there promising research trying to tackle that memory issue? That sounds like a big blocker for complex proofs.
Yes, definitely. Folding schemes are one exciting technique mentioned in the sources. The idea is to incrementally compress the representation of the computation as it proceeds, folding each step into a running summary.
So you don't need to store the whole history.
Right. It directly addresses that space problem, making proofs for longer computations more feasible. Companies like LurkLab and Microsoft are actively working on these kinds of techniques. And finally, you still have the inherent privacy versus performance trade-off. Sometimes stronger privacy guarantees or more complex features can add overhead. And as we discussed with hardware acceleration, the raw proof generation speed still needs dramatic improvement for widespread, real-time adoption outside of specific niches like blockchain rollups where latency is more tolerable.
Okay. Given these challenges, are there other technologies on the horizon that researchers are watching, things that might complement or even challenge ZKPs down the line?
Well, the elephant in the room for all cryptography is always quantum computing, though practical code-breaking quantum computers still seem a way off. But another area mentioned is fully homomorphic encryption, FHE.
FHE. That's the one where you can compute directly on encrypted data without ever decrypting it, right? Sounds similar to ZKP goals.
It sounds similar, but they actually tackle different, though related problems. ZKPs focus primarily on verifiability, proving that a computation was done correctly, often on private data. FHE focuses purely on privacy of the computation itself, allowing computation over data that remains encrypted throughout the entire process.
So ZK is about proving correctness. FHE is about computing on secrets.
Basically, yes. ZK proves that it happened correctly. FHE ensures what happens stays secret during computation.
But the sources suggested they might eventually work together. Could they be combined?
That's the really exciting prospect for the future of confidential computing. Imagine combining the strengths of both. You could use FHE for the actual private computation on encrypted data, and then use ZKPs to generate a proof verifying that the computation was performed correctly on that encrypted data without revealing anything about the encrypted inputs or intermediate results.
Verifiable computation on encrypted data. Wow, that sounds incredibly powerful.
It does. So despite the challenges we've discussed, it really does feel like there's a huge amount of energy and momentum in the ZKP space right now.
Yeah, the sources definitely conveyed that feeling.
Absolutely. They paint a picture of a field experiencing what some call a Cambrian explosion.
A Cambrian explosion that's a vivid image,
Mm.
like a sudden burst of diversity and innovation.
Exactly. We're seeing huge funding rounds pouring into ZKP startups. Over $725 million in 2022 alone was mentioned. There's a surge in academic papers, massive activity on open source repositories like GitHub, and literally millions of ZK proofs being verified daily on networks like Ethereum via ZK rollups. The activity is undeniable.
So it's moving fast.
It really is. Looking forward, active research areas include developing more lightweight ZKPs proofs that are cheaper and faster to generate, maybe suitable for resource-constrained environments like IoT devices, and further integrating ZKPs with machine learning, especially for larger, more complex models, is a huge frontier.
And moving beyond blockchain.
Definitely. The potential for ZKPs to impact a vast array of industries outside of crypto and blockchain is immense. Resources like Ingopedia are even emerging to help people track and understand this complex but fascinating space.
Well, we've certainly taken a deep dive today. We've traced the journey of zero-knowledge proofs from their mind-bending core concept through the intricate mathematical engines that power them, the essential infrastructure and hardware enabling them, and finally, exploring this diverse and rapidly expanding landscape of real-world applications where they're already making a tangible difference.
ZKPs truly represent one of the most significant breakthroughs in modern cryptography, I think. They offer this unique capability to build systems based on verifiable trust without demanding the surrender of sensitive information. That's a powerful combination.
It really is. It feels like a field that's not just theoretically interesting, but one that's attracting serious investment, finding real business applications, and seems poised to reshape fundamental aspects of our digital lives.
Which brings us to a final thought for you, the listener, to consider as you wrap up this deep dive. Given the power of zero-knowledge proofs, this ability to prove something is true without revealing anything else about the underlying data, how might this technology fundamentally transform your own digital interactions in the coming years? Think about how you currently interact online, proving your identity, verifying information you see, making transactions, interacting with AI maybe. What specific aspect of your digital life could be dramatically improved, made more private or more secure if you had this capability? If you could prove a crucial fact or condition without being forced to reveal all the sensitive data behind it, what could that unlock for you?